Yes. So there are a few things before we discuss whatever you want me to discuss. So let's start by doing assignment 3, by discussing assignment 3, because I have uploaded the lecture for assignment 3. Okay. So if you see the lecture, this lecture basically has the entire parser. This lecture has the entire parser. So it also has a symbol table, scope resolution, and all those things. Scope resolution, symbol table. You need symbol table, but you don't need scope resolution for assignment 3, right? So you may not use scope resolution, but symbol table you might choose. You can implement your own way, or you can choose to implement this way. But this will work for project 2. It won't work for project 3. Right? But this is uploaded as a guide. Now, in here, what I have done is the parser is here. The type checker is not there, but the parser is here. So if you go and um, so all these are related to symbol table and scoping, searching the symbol table and so on. But if you go here further down, this is the parser. Right? This is the parser which checks for real num. So you can have real num. This is also, it checks for switch cases. Let me check where. So it parses variable list, parses the body, unary operator, binary operator. All these are new for assignment 3, right? So it parses all these unary, binary, parses the primary, it parses expression, assignment statement, parses switch case list, switch statement. So it has all the parser, while statement, if statement, and so on. So it has the parser, but it does not have the type checker. Right? It also does not have the logic to take a variable and put it into symbol table. And it implements a symbol table. It has add list, delete list, those things. But it does not have the logic to take a variable and put, or when will you put a variable in the symbol table, or when will you search the symbol table, where will you stop the search. All these things it does not have. Right? It only has the parser. So what you can do is you can start from here, or you can start from your project 2. So this is only as a guide. This, if you try to use this on assignment 3, it won't work. It will throw a lot of errors. So don't try to compile this and run, but look into this if you want hints on the parser. Then I uploaded the sample final exam. So when, oh, this one. So I've uploaded a sample final exam. You can find it in practice exams, final exam sample. But you can find it there. I will also upload the solution, but later. So we can discuss this, or we can discuss any other questions that you have, because I don't want to discuss this right now, because I want to give you some chance that you do it on your own first. So, but let's see the format. The format is, it's a comprehensive exam. This is the last year's, no, it's the spring 2016 exam. So the format will be the same. So here you have first some regular expressions. So this is something that is from the midterm. Then first and follow is also something from the midterm. But then comes the other stuff. So you have C scoping, static and dynamic. Then you have stack allocation. No. Oh, so memory locations, what are garbage or not, those things. Then you have type checking. How can you check the type or so this will be the format where I will give you the abstract syntax tree of a particular function, right? And you have to determine or you have to answer the following questions like what is the type of A, what is the type of B, type of C, D, and type that if returns, right? So all these things you have to infer. Now you should not just write them, you should explain also why you inferred those types. So if you just write them, then you won't get full marks. And that is what I have done for midterm as well. People who have just written the answers, I haven't given full points. If you don't explain, then no points. And some points because of correct answer, but not full points. Then I'll give you this C code, which is of you'll assume static scoping. You have to answer these questions: that what is the output of the program? If you pass by value, then pass by reference, and then pass by name, right? Then you have some lambda expressions, and there will be beta reduxes, right? In lambda expressions, the last class we saw beta reduxes. So you will have to apply those reduction techniques, beta reduction techniques, to reduce into the beta normal form. Beta normal form means there are no reductions left. So these are some sample questions. What I can do is I can omit the first and follows it because we have done those for a long time. So I can omit those and maybe add some questions related to runtime execution or something like that. Yes.
Is the final going to be more centrally focused on the material that wasn't on the first exam, and then like maybe have a question from some of the old exam?
Yes.
Okay.
But mostly it will be heavily on the latter half. So you can see that there are 7 problems and 1, 2, 3, 4, 5. 5 of them are from stuff after the midterm and 2 from stuff before the midterm. So I like to keep some before the midterm as well because some students might have great concentration up to midterm and then they lost focus. So if you have great concentration up to midterm, then you can get full points for the questions before midterm, right? So that's why I like to keep some questions. Now here I told you to answer all of them. Did I tell you to answer? Yeah. Here I told you to answer all of them. Maybe I will keep some questions that you might choose to answer. Right. So I will have more questions than you need to answer. Okay. So now you tell me what do you want me to discuss first? What do you want me to discuss?
Pass by name versus reference and value.
Pass by name versus reference and value. You said then she was saying runtime execution engine. So runtime execution, pass by value, name, reference, and then what else? Any other suggestions? We'll come up with suggestions later. So let's discuss the pass by value, name, and reference first. So let's do this final exam question then, because we already have it here. So can we take 2-3 minutes to do pass by value? Pass by value should be easy. Let's take 2-3 minutes to do pass by value. So I'll make it bigger. How can I make it bigger? Okay. So can you do pass by value for 2-3 minutes? I'll do it on the board. Because I already have the solutions for this. I'll put the solutions. So you don't need to open the board. If you have an answer, you can raise your hand. Okay, anybody with an answer for pass by value?
0, 0, 1, 2, 14.
0, 0, 1, 2, 14. Anybody else with the same answer? Anybody else with the same answer? You have any different answer? Okay, anybody with a different answer? Okay, let's see how. So x is 0, a 3 is so 0, 1, 2, that's the array A, and B we don't have a value. Now B goes to foo x comma ax. So x here is 0. So actual arguments or actual parameters of foo is foo 0 and ax, right? So 0, 0, right? So this is passed by value. So if it is 0, 0, then what happens? Okay, 0, 0, then a is 0, c is 0, x, y, a, x is equal to a plus c, right? So a plus c, so x becomes 0 inside foo. So inside foo x is 0, a is 2, y is 0, c is -1, and you return bar a. So now bar a means bar 2, right? So 2 is the actual parameter. If you have bar 2, then bar 2 is what? You do y equals 10 and y plus 4. So 14. Y equals 14. Now you return 14. So if you return 14, and this also returns, so foo returns 14, b becomes 14. So then you print x. So x is this mains x. So x is 0, then a0 is still 0, a1 is 1, a2 is 2, and b has the value 14. So yes, pass by value is fixed. Now can you do pass by reference? Let's see what happens. Do pass by reference. Let's take, no, for pass by reference we might need some more time. So let's say 4 minutes. Let's take 4 minutes to do pass by reference. Anybody with an answer yet? Let's take one more. Anybody else with an answer? Nobody? Let's try to do it. So, what is pass by reference? Pass by reference means that the formal parameters of the function that you're calling, and so when you are calling, you have to use the actual parameters, right? So the formal parameters of foo are bound to the location associated with the actual parameters. That is pass by reference. The formal parameters of whatever function you call is bound to the location associated with the actual parameters. So what you first have to do in order to answer that question is whenever there is a function call, you have to draw that box and circle diagram. Right? So you have to, so the first function call is foo x ax. So in that case, you will have x, for x you have a box and circle. And also for ax. So in this case, what is x? X is 0. So a0 also has a box and circle diagram for it. Similarly, a1, a2 and a3 will have it. Okay? Similarly, a1, a2, a3 will also have their box and circle. But let's say that is our box and circle. Now you call the function foo int ac. So you know that there is an a. For a, there has to be a box and circle. But for pass by reference, what we did was we didn't define a new box and circle. We just referred to the same location as the actual parameters. So x is an L value here. So it cannot be numbers. You cannot send in numbers because numbers are R value. So if you are doing pass by reference, you have to have L values as actual parameters. Right? You cannot pass numbers. So L values, so we have L values, foo x, ax, both are L values. So here a is bound to x, right? Yes, a is bound to x. So instead of having a new box and circle, a is basically bound to the same box and circle of x. C is bound to a0, right? C is bound to a0. Now you call foo int ac. So in here you define new variables x. So x becomes a plus c. A, so okay, so value of x was 0 initially, and value of a0 was 0, right? That's what we had. Now you have x equals a plus c. So a has a value 0, c has a value 0, x equals 0. So this is in foo. This is inside foo. Then you have y. Oh no, then you have a. A equals a plus 2. Now what happens? A is this location, right? So a's value was initially 0, a became 2. So this one now became 2. X now became 2. So instead of 0, now x became 2. I'm drawing the circle again, but this is wrong. I mean, you shouldn't draw two circles for the same location. I'm just updating it, right? So if you do this in an exam, you'll get 0. Don't do it in this exam. Just redraw it, right? So now x has 2. Okay. So now you do y equals c. Y equals c means c was this, so y became 0, right? And now you do c equals y minus 1. C equals y minus 1. So y is 0, c became minus 1. C was this location, a0. So basically, this again becomes minus 1. Now this is interesting. Now you do bar A. So if you do bar A, you know bar has a int y, right? So it has to have a y. So now we are doing bar. Right? Let's do it. So bar has y. Now this y will be bound to what location? It will be bound to that location of A. A is an L value, we know. So A is which location? A is again x. So this y is again bound to this location. Then inside bar, what you do? You make y equals 10. So basically instead of 2, now you have 10. And then you return y plus 4. So you return 14. Now here you don't change any value because you haven't done any assignment yet. So you don't change any value. So you return 14. Now that also returns. So foo returns 14. B becomes 14. Right? Inside main. So inside main, B becomes 14. Now you print out. So you print x. X is which location? That. So you will first print 10. Then you print out A0. A0 was -1. Then you print out A1. A1 didn't change. So A1 is still 1. And you print A2. A2 didn't change. So A2 is 2. And you print out B, 14. Okay. So that is your pass by reference. Do you understand how it happened? Any doubts?
In bar, how did y get bound to x again?
Because of pass by reference. Because bar did bar A, right?
Mhm.
So that means the formal parameter y is bound to the location that is for A. Now what was location for A? Location for A was here, x. Right? That is pass by reference. Any problems with that? Okay. Now let's do pass by name. Now that will take even more time. So let's just do it. We won't wait. Let's say pass by name. The pass by name is going to be messy. So now what you have to do is you have to do textual replacement. So you do foo x ax, right? So let's rewrite foo. So foo became x ax. So this is x. You don't have to have x. Int. So this is x, and int c is ax. So what it means is that every occurrence of A and C, you have to replace it by AX and X. Now note that there is some int X and Y there. So one good thing to do, as suggested by another student, is just rename this. Maybe make it X dash. Right. Then you have int Y. Then you are making x equals a plus c. So x dash you are making equal to x plus ax, right? Then a equals a plus 2. So a is what? A is x. You are making x equals x plus 2. Then you made y equals c. Y equals ax. Then we made ax equals y minus 1, right? So you reload this function. Oh, then you have to return. So then you say return.
Shouldn't we replace y with ax in the assignment before return there? Because ax is equal y minus 1 and y is already ax.
No. No. We are not supposed to replace y by ax. We are not supposed to textually replace y, because y is a local variable in foo. We only textually replace a and c. We don't replace y, because y is not a and c. Y is not the formal parameter, right? So that's why we don't replace. So then you return bar a. Now a has to be replaced by x, right? So you say bar x. Now this is also another pass by name call. So if you do pass by name call here, then what you do is you have bar x, and you say okay, x equals 10, and you return x plus 4. Okay. Now let's analyze. So x was 0, it was 0, 1, 2, and b we didn't have any value. Now we call foo x comma ax. So x was 0, ax, so x is, since x is 0, a0 is 0, right? So let's come here. So x dash became x plus ax. So which means x was 0, ax was so a0. So 0 plus 0 is 0. So x dash became 0. So this is 0. Then we did x equals x plus 2. So x became 2, right? Now y is ax. So this is a2, basically a2, right? So if this is a2, then y is what? Y is 3. Y became 3. Then we say that ax equals y minus 1. So this is a2. So a2 equals 3 minus 1, which means 2. So a2 became 2. Now we made a mistake. A2 was not 3. 2. A2 was 2, right? Yeah, you should tell me these mistakes. A2 2, so then y1, so this becomes 1. A2 becomes 1, right? Now you return bar x. Now x was 2. So x is 2 here. Now you made x equals 10. So x became 10. You return 14. Right? You return 14. So now you come back, you want to print. You want to print. You print x. X is 10 here. You return 10. Then a0. A0 is what? So we didn't change a0. So a0 is still 0. A1. We didn't change a1. So a1 is 1. Then we did a2. A2 is 1. Right? A2 is 1. And then b, we have 14. Yes. Any doubts with pass by name? Yes.
Shouldn't we delay a replacement until the last possible moment? So shouldn't we use the results of bar to replace the assignments in full?
No. Because the execution follows this. The execution follows this sequence. After doing all this, then you call bar and you return the value. So you should not calculate these, or you should not use these or evaluate these assignments following what bar does, because bar comes later. Any doubts with pass by name? Okay. So if there are no doubts, that's the answer. I post these answers. Let me take a picture of this one because I think the pass by name that I did is not correct. Now she said we should discuss runtime execution. So I don't have an example in this. What should we do? I don't want to use this example because there is printf. Printf confuses a lot of things. Like what happens to the stack when you call printf is very weird. So I want you to use that example. So what example can I use? Let me see. So what exactly do you want me to discuss for runtime execution? Just go over it again? Okay, so then we can use the same example that is in the slide. So you wanted stack. What do we do to the stack? Okay. So let's. What was the- Let's start with this. Oh, with this. Let's start with this slide. So, what are the components of a function? Function declarations have function name, formal parameters. In the formal parameters, you have names and types, and you have a return type, right? Now, when you call a function, what you do? You call like f equal f x1, x2, xk. x1, x2, xk can be parameters, or can be variables, or they can be numbers, or they can be expressions. So these x1, x2, xk are called the actual parameters. So there is this difference: formal parameters and actual parameters. Formal parameters means when you are declaring, you have to have names. You cannot have expressions. You cannot have numbers when you are declaring. So when you are declaring, you have some names and some types associated with those names. So those parameters are called the formal parameters of a function. Now when you are calling a function, you can replace the formal parameters using actual parameters. So those actual parameters can be variables, names, you don't need types, it can be numbers or constants, it can be constants, or it can be expressions, right? Now, you know that every function, corresponding to each function, there is its separate space in the stack. Each function has a separate space in the stack. A main program has a big stack, right? And in that stack, whenever you call a function, each function has its separate stack, separate portion of the stack. That portion of the stack is used to manipulate the actual parameters, local variables, and also other things such as pointers or instruction lines and all those things. So a function has to have its own portion in the stack. That portion is called a frame, function frame, right? So each function has a function frame. So what are function frames? It allows us to allocate memory for the function's local variable. Not only that, it allows us to do a lot of other things. So function's local variable, actual parameters, addresses, memory addresses, right? Instruction pointers, as well as stack pointers, base pointers, all these things we can store in stack. However, we need to call a function before it starts executing. So when considering calling a function, we need several other information. We need return value. Where will the function, a particular function may or may not have return value. But if it has a return value, where will you store it? Right? Then it has the actual parameters, frame pointers. Frame pointers is very important. What is frame pointer? Frame pointer says when does one function's frame start and other function's frame end. In the stack, there has to be a way to delineate that, okay, this particular portion of the stack is function 1, the next portion is function 2. How do you determine? You determine using the frame pointer of a function. Every function has a frame pointer. From that frame pointer downwards, it's function's frame, unless you hit another frame pointer. So from one frame pointer to the other frame pointer is the function's frame. So using frame pointers, we have to we can demarcate the portions of the stack for a given function. Then we also have to keep executing a program. So when you execute a function and it returns, what do you do next? You have to keep track of what you do next after you return for a function. So the return address, which instruction do you execute right after the function returns, that also has to be stored somewhere, and it can be stored in the stack. Then it has local variables, and it might also have some temporary variables, there's constants, a plus 2.5, and where do you store the 2.5? So all these things are part of function frames. Now, these are certain duties that you need to perform, right? So you have to have calling convention. Calling convention means who performs these duties. There are two entities, the caller and the callee. The caller calls a function, and the function that is called is the callee. So who takes care of what here? Does the caller take care of all of this, or the callee takes care of all of this, or do they share responsibility? Depends upon the designer of the programming language, right? Or the runtime execution engine. Depends upon the designer. So you can have all these taken care of by the callee, that's fine. You can have all these taken care of by the caller, that's also fine. But what is done in Linux is that you share responsibility. So how do you share responsibility? So this is the Linux calling convention. So caller does these two and callee does these four. So what does caller do? And caller does that in order, like in sequence. It doesn't do in the reverse sequence. It has to do in the correct sequence. So what does the caller do? The caller pushes the arguments of the function that is calling in the reverse order into the stack. So it pushes the arguments into the stack. And then it also pushes the instruction that has to be executed next after returning from the function. It also pushes that instruction into the stack. So these are the two responsibilities of a caller. Right? Push the arguments, push the next instruction that is being called. Then what does callee do? Callee takes care of all four things. So what the first thing that callee does is that it takes the frame pointer. So now remember, callee's frame pointer is not yet assigned. So whatever is in the frame pointer, that means it was the frame pointer of the caller, right? Because callee has not been assigned a new frame pointer yet. So callee pushes that previous frame pointer onto the stack. So which means it stores the function frame of caller, right? It stores securely. Then what callee does is it creates space on the stack for its local variables. How much space depends upon the designer. But it has to be at least the total number of local variables that it has, at least, right? So it creates space on the stack, ensures that the stack is consistent on return. So what does it mean by that? Callee, at the very least, changed one thing in the stack. It pushed the frame pointer onto the stack. At the very least, it will always do that. It might not create space for its local variables because callee might not have local variables. If it does not have local variables, it did not create space in the stack, right? But one thing is for certain, that callee will push the previous frame pointer onto the stack. So it changed the stack, right? Callee changed the stack. It's the responsibility of the callee to reverse that change. You have to reverse that change. So that's what is the responsibility of callee. It ensures that the stack is consistent on return. When you return, you have to leave the stack as it is, as was changed by the caller. And then finally, if callee has a return value, it has to put that return value into the EAX register, CPU register. Right? EAX CPU register. So that is the convention. Now let's see an example. Let's directly go to the stack. Okay, so this is the setting. This is the assembly level code for this code. So that's the simple code. There is a main and there is a variable inside main a, and a is equal to callee 10, 40. 10 and 40 are the actual parameters. And remember, these are constants. So these are not local variables. These are temporary variables. 10 and 40. Right? These are constants. So and then you return a. So you call a and b, and when you go into a and b, A and B are formal parameters of quali, and then you return A plus B plus 1. So remember, quali does not have any local variables, right? Quali does not have any local variables. So now let's understand what happens. So these are the addresses for the lines of code. So when you have a program, we have discussed this million times before, not million, maybe 10, 20 times before, that whenever you want to run a program, you have to give memory to 4 things: code, global data, stack, and heap. So this is memory for the code, right? You compile the code, put it into machine language, convert it into machine language, and you get memory. So these are actual physical addresses. Those are physical addresses. So you, if you access that address, you'll find that code in memory, in RAM. You'll find it. So let's say those are the addresses. Now you see that at the onset, you can realize that these addresses don't increment by 1 all the time. The first one increments by 1. From A5 it goes to A6. The second one from A6 it goes to A8. 2 lines, 2 memory lines. This is because every code in every assembly level code has a different size, right? It has a different size. Now why does it have a different size? Because some line of code might need arguments. If you need arguments, you need to store the arguments in some lines, right? So the moment a function starts having arguments, then you need more lines to represent that assembly level code. So that's why that it takes the sub assembly level code takes 2 lines, because you have the register ESP and you have that 0x18, you have to store it somewhere. 0x18, you have to store it somewhere. So remember, sub has its unique hex code. It's a 32-bit code. 0x18 is also a 32-bit representation. So you cannot store both in a 32-bit line. You have to have 2 lines to store sub and its argument. That's why from A6 you go to A8. This we haven't shown. This is not really how it's represented in RAM. This is just for your visual ease. We have represented it in this way. But if you see the RAM, you will see that 0804838A7 has 0x18 and 0804838A8 has some weird hex number. That hex number belongs to the assembly code for sub. Right? So it's 2 lines of code. Now, corresponding to these 2 lines, an internal thing that happens. Now I'm going a little bit off topic, but it's good to know. An internal thing that happens is that every assembly level instruction might require 1, 2, or 3 clock cycles. Right? So they might require varying levels of clock cycles. Ideally, you should have 1 instruction per clock cycle. That's the fastest CPU that you can have. Right? But certain instructions also need more clock cycles. Turns out that more the length of the instruction, more number of clock cycles it takes. Right? But that is side information, you don't need to know that. But regardless, so coming back to the topic, these are the addresses. These are the actual physical addresses of lines of code. Now let's see what happens. So initially, now you have to remember, so that is the stack, big stack, or empty space. These are all the registers. EAX has to be the return register. EBP is the base pointer. We know we store the frame pointer there. EIP is the instruction pointer. So this is the it is the address of the next instruction that we are going to execute. ESP is the stack pointer. It's the address of the top of the stack. EDX is a register where we store some temporary variables, temporary or permanent variables, but it's a register to store variables and do computation. Right? Now you have to remember that this is a yes.
What's the difference between the stack pointer and the base pointer?
Okay, what is the difference between stack pointer and base pointer? It's a very good question, and we discussed this before. Initially, when a program runs, stack pointer is same as the base pointer. when not a program, sorry. Initially when a function runs, at the start, you haven't yet executed the first line of code of that function, then base pointer is same as stack pointer. But when you run the function and it starts changing the stack pointer changes, but the base pointer remains the same. You never change the base pointer. So base pointer basically holds the frame pointer, which means it holds at the start of the function frame. So by checking the base pointer, you can check when the function frame started. But the stack pointer roams around. It roams around. So you can change the stack pointer, but base pointer remains the same. Right? So that is the distinction between stack pointer and base pointer. Do you understand? So let's okay, now before we go into this, we have to remember that this is a user program. That you have written this code. In order to write this, or in order to start this function, what do you need to do? If you want to start executing your code, what do you need to do? Before executing your code, what was happening in the CPU? Now, let's say you are not running any program. Let's say you are not running any program before executing this code. What was happening when you are not running any program?
Some program called me.
So what program was that? If you are not running anything, what is the CPU doing? CPU is not sleeping. CPU is doing something. What is it doing? No ops. It is running a program, and that program has no ops in it. Right? So it's doing nothing basically, but it's still doing something. So it's executing no ops. So remember, when you are calling your code, basically that main that you are calling is a function call. So main itself is a function call. It is being called by some other process that was running before yours. Right? Typically it's an interrupt. You take an interrupt and you run a different program. Right? So at least an interrupt has an interrupt service handler. Right? So that interrupt service handler itself is a function. So you run that function and that function calls your function. So when main is getting called, main is itself a callee. Right? Somebody else is calling main. So main is itself a callee. So first we have to understand what is the responsibility of a callee. There are 4 responsibilities of a callee for main. Right? So let's understand what are those responsibilities. So the first responsibility was actually it would have been good if we have a responsibility in that, and then the stack here. How can I do that? This is so. Yes. So that's the responsibility, and this is our code. So what is the first responsibility of callee? It has to push the previous frame pointer onto the stack. So what does the first line of main do? Pushes EBP. What does EBP have? The EBP has the frame pointer of the previous function, right? So that's why you do that. So let's say the stack pointer of the last function was a D2, D4. Let's assume, because we don't know. And The next instruction that we want to execute is 80483A5 because we have to execute that, right? So you need to push EBP. Now, what was the value of EBP? You don't know what is the value of EBP. But if the stack pointer is FD2D4, then we can assume that the previous pointer did something to the stack. Either it did something to the stack or it didn't do anything to the stack. If it didn't do anything to the stack, then base pointer is same as stack pointer. Frame pointer is same as stack pointer. But if it did something to the stack, then that means stack pointer is more than the frame pointer. So EBP should be always less than equal to the stack pointer, right? So that's why let's assume some value of EBP. We don't know, but let's assume that EBP was FD2C0. Let's assume. We don't know what it is. So now let's start executing. If you execute push EBP, now what does push do? What is the first thing that push does? Decrements. So push should decrement. So see, from FD to D4 it became FD to D0, right? So FD to D0 means the pointer goes down and you take the value what is there in EBP, you put it in there, FD to C0, right? Then what is the next responsibility of poly? It's actually not there because the next responsibility of poly was it has to take care of its own frame pointer, right? It has to take care of its own frame pointer. So how does it take care of its own frame pointer? So where is the frame pointer now? Wherever the other function stack ends, that is the start of the next function's frame, right? So that's why whatever is in ESP, that is the frame pointer of main. So that's why it moves ESP to EBP, right? So ESP is now FD to D0. So remember, up to FD to D4 was the stack of other function. Then FD to D4 has the base point or frame pointer for the other function. Now FD to D0 is for the stack from which my function starts or the main function starts. So that's why you push that or move ESP into EBP. So EBP becomes FD to D0 now. Now if EBP is FD to D0, that is the start of the frame, right? Then comes the next responsibility, that you have to create space on stack for local variables. Now, what local variables does main have? Main has what? A. Main has A, and it also has two more local variables. Not two local variables, but temporary parameters, 10 and 40, right? Because it has to push those variables into the stack. But as of yet, main is not the caller. Main is still the callee, right? So it makes space for those variables, those temporary variables, as well as A. So it subtracts 18, which is 24, right? It's 24. I have no idea why 24, but it is at least more than 16, right? So I have no idea why it is 24. It's what the compiler decided, but at least it's more than 16. Then what it does, now the next code for main is calling that caller function or callee function, right? It's calling the callee function. So since it's calling the callee function, it has to move the arguments in reverse order into the stack, right? So that's why what it does is that it first it already created space. So once it does create space, what happens? Stack pointer becomes FD to B8, So that is the scenario. Now you are executing the next instruction, which is 8048AB, which is move ESP plus 4 and move it into move 40 into that. So ESP plus 4 is FD2BC, and you move 40 into that. Then you move 10 into ESP, so you move 10 here. Now you are calling, right? Now this next instruction is kind of complex. So there are a lot of things that are happening for call. First of all, when you are calling, you have already pushed arguments onto the stack. Now before calling that function, now main is a caller. So main has to also push the address of instruction after call into the stack. That is the other responsibility of caller, right? So how does it do that? So first thing that call does is that it pushes the EIP into the stack. So what is the EIP now? So since it has to push, so it has to first decrement. It first decrements, so which means stack pointer becomes FD2B4, and then it takes the EIP next instruction, right? 80483BF, puts it there into the stack, and then updates the EIP with the argument of call. So three things call does. Call first pushes the next instruction. So in order to push the next instruction, it has to decrement first, decrement the stack pointer first. Then it takes 80483BF and puts it into the stack. Takes the argument, puts it into the instruction pointer. Those are the three things that call does. Now when you execute the next instruction, you'll automatically go to that calling, right? Because EIP is this. You automatically go to calling. Now what does callie do? Responsibility that it has to push previous frame pointer onto stack. That's what it does, push EBP, right? So if it pushes EBP, then the stack has to again decrement, right? So it becomes FD2B0. So it decrements the stack and it takes whatever is in EBP, that is FD2D0, and puts it into the stack. Now callie has to have its own frame, right? Callie has to have its own frame. So how does callie has its own frame? It just moves the stack pointer into the frame pointer, because whatever is after stack pointer, that is callie's frame, right? So it moves ESP to EBP. So ESP was FD2B0, EBP became FD2B0. So now that is main's frame, and this entire thing is callie's frame. Note that callie does not only have whatever is under the stack pointer, but it also has those arguments. These are arguments of callie, right? So since those are arguments of callie has access to those as well. So callie's frame starts from the arguments, whereas main's frame starts from the line above those arguments, right? So that's how you demarcate, by using the stack pointer as well as the frame pointer. By using the stack and frame pointer, that's how you demarcate. Now let's take the next step. So we want to do a plus b plus 1. Now since there are no local variables in callie, so you don't need to create any space. So that's why we didn't move the stack pointer below. We didn't subtract the stack pointer, right? So that step we skip because we don't need to create space. Now you do a plus b plus 1. How do you do a plus b plus 1? First you do a plus b and then you add 1 to it. How do you do a plus b? You take whatever a is, put it into ex, whatever b is, put it into edx. How do you know what is a, what is b? The way that you know is you use the frame pointer. With rest, you know that frame pointer is where my frame starts. Right above the frame pointer is the instruction where I have to return to. Right above that, I have my first argument, and right above that, I have my second argument. If I have 4 arguments, then right above the second I have third, above the third I have fourth. So by knowing the calling convention, the callee exactly knows where are my input arguments. Because the callee knows that frame pointer, then on the top of it, I should expect the instruction pointer of the previous column. Then on top of it, I should expect all my arguments. Right? Because the calling convention is fixed. So callee knows the calling convention. That's why with respect to EBP, it starts addressing. Right? So for what does it do? First, it knows that EBP, on top of EBP, I have the frame pointer of the previous function because I already pushed it. No, that is ESP, sorry. Oh no, because I moved ESP to EBP. Yes, so on top of EBP, I first have the frame pointer of the previous function. Then I have the instruction pointer, and then I have the arguments, right? So since I have the frame pointer, instruction pointer, and I have 2 arguments, the second argument should be in EBP plus C. So 4 plus 8. So plus 4 if I do, then I get the frame pointer of the previous function. Plus 8 if I do, I get the instruction pointer. Plus C I do, I get the my second argument. Then if I do plus 8, I get my first argument. Right? So that's how it knows. So plus 8 plus C, those are the 2 instructions that it does to load A and B into EAX and EDX. Then it uses this function LEA. What does LEA do? Basically, it multiplies EDX with 1 and adds EAX and stores the result in EAX. Right? So it does that. So now my EAX has 32. Right? Nothing happens to the stack. You add 1 to EAX, EAX becomes 32. Nothing happens to the stack. So everything is done. Computation is done. Now, and also the return value is in EAX. Computation is done, return value is in EAX. So fourth responsibility of callee is done. Return value is in EAX. Now we come to the third responsibility. We have to reorder the stack. Right? We have to reorder the stack. How do we reorder the stack? First change we did to the stack is we pushed the EBP. So callee has to pop it. So you pop the EBP. Now remember, what was the first thing that was there in the stack? That first thing was the frame pointer of the previous function. So if I pop that into EBP, then that means I am restoring the frame pointer of the previous function. Right? I am restoring the frame pointer of the previous function. So that's why you pop into EBP. So when you pop into EBP, you first take the value FD to D0, put it into EBP, and then increment the stack pointer. Right? FD to D4. So frame pointer now is there, and stack pointer is here. Right? Then you do the return function. Now return is again another interesting function. Return. So what does return first do? Return first changes the EIP. How does it change the EIP? It just does pop again. It pops it into EIP now. That we haven't shown here because it is internal to return function. So return function first pops the EIP. So pops the stack, puts it into EIP. So at the top of the stack you had 80483BF. Now notice that is the EIP. There's the next instruction of main that you want to execute. So if you pop it into EIP, then next time you execute the next line of code, that will be the line of code of main, right? So you pop. So if you pop, you take that value 80483BF, put it into EIP, increment the stack. Right? You incremented the stack. Then what you do is you have to still you have to redo, because you know that this is not the stack pointer of main. So the stack was the okay. So in the when you do return, before you do return, now it is reverted back. Right? Everything is reverted back. That is how we left main. Our stack pointer was here and the base pointer was there. That is how we left main. If you see, let's go back and to the point where we called callee. Exactly same scenario, right? So when our arrow was here, we had this as our no, before calling. Yes, before calling. Before we executed call, we had this as our stack. Now after we execute call and we return, let's see what we have in our stack. We have some values here, but the stack pointer and frame pointer are reverted back. Right? So everything is reverted back. Callie's responsibility is done. You go to this. Then you take the result EAX, move it into EBP, and you then take the EBP and move it into EAX. Now you leave. Now leave has other semantics. So what do you do when you have leave? What you do is you take. Wait. So ESP was FD2B8, right? So what you now do is you take FD2B8 and you move it into the base pointer. So move the base pointer back to stack. So stack and base pointer now becomes the same, FD2D0, right? And then you do the same thing with return, the one that you did for calling. So that is how the stack works. Now the thing is, in an exam, I won't ask you to do the entire program. What I will do is, I will maybe say, okay, if you execute that line of code, what happens to the stack and base pointer? Or if you execute these three, what happens to the stack and base pointer? So I won't tell you to do all the entire code, just 2-3 instructions, and ask you what happens to the stack. Right? But in order to do that, you should understand for the entire code what happens. Do you have any questions? Any doubts? You have doubts? Anything else you want to discuss? We have just 4 minutes. We can go early. Oh yes, you have something.
Real quick, it might have something to do with call, but when we're moving EAX into an offset of the base pointer, why didn't we just make the stack pointer equal base pointer and then do that and then put the
Could have done that.
huh?
Could have done that.
Okay.
But that's how it works.
Oh. Okay.
So that is the decision taken by the runtime execution. Don't rely on that because I don't know yet.
Okay.
If there are cases that we got very low marks, so like a lot of people got very low marks in all that, and then I will take it.
Okay. So it could be. Okay. Thank you.
Scottsdale.
Just assume. Just, even if you are not correct in assuming, you have to correct.
Thank you.
You can use my lecture, but that won't work as it is. You have to say, because it will throw a lot of errors.
I have the shift instruction and stuff like that.
Yeah.
This process.
I can't do that myself, but I won't
And
try.
then,
Alright, I'll
are
try.
you using the semaphore then? Oh, like.
You can choose not to match self
P and V has to be implemented using shape.
But I need the money, so.
But yes,
P and
I
V.
understand
to be
that.
implemented using shape.
Yeah.
And then I said, wow, like, yeah, E equals 0. Or basically, I would start with log. Yes, I would do
Yes,
this.
yes,
It's a nice, nice.
yes.
I see. Then I would still like this part.
You have to see, I cannot tell you.
I don't know, so I mean, do I need this at all in order to, because the question's very general.
So, you have this void, right?
Right.
So think about how can you represent the minus minus using shape.
I would basically say shift E or star B minus 1 and then. Okay.
You could do that.
So then, is that all that it wants? Because that's.
So,
all it's asking.
so you think about it. Whether that is all that you need to do.
You could do a lot. I mean, it says implement it with semaphores.
Yeah.
So you could do like a full, like really get into detail, writing the code for it.
Do you need that data?
I don't know. I don't know what you're looking for. I mean,
So I am looking for a method that you implement PS using shape. So PS is what? Somebody does, if S is 0, it blocks, and if S is not 0, it does S minus minus, keeps waiting.
That's it. Okay.
So you have to just implement those two functionalities using shape.
Just going back to that email I sent you all ago, if needed, I can come to your office hours today. But
What even?
it was a while ago, and I can't remember the other time I talked about it. It was about my Senate one that was remember C++ 11 thing that wasn't working.
Oh, okay.
Right. So
Come to my office hours and I will.
awesome. Today,
Yes, today you can come to the office hours.
3 to 4, right?
2
2
to 3.
to 3. Okay. And
And then we can see what is wrong.
awesome. And it's in the same place you were last time, right? Awesome. Next to your next to
You
TA.
won't meet the TA because the TA he has some problem.
Yeah, I figured so. So I'll meet you there at 2.
Okay.
Awesome. Thank you very much.
Okay, no.